Okay, class, let's finish the 12th chapter. Before that, I'm going to discuss something related to the quiz that I assigned you. In the quiz, I asked you the question where I gave you a beam and there is a pin joint on the left, the roller on the right. I gave you a moment 3 kilonewton times meter. I think numbers may change from student to student. So let's say this is A, let's say this is B. So because this is a pin joint, we'll replace the pin with AX and AY. Pin joint allows free rotation, so we don't have a moment reaction. And here we have BY. And it is given that this is at a distance 1.5 meter. Again, the numbers change from student to student. This is 2.5 meter. I gave on the similar terms in the quiz. So to solve this problem, you have to apply equations of equilibrium, which is sigma fx equal to 0. That implies ax is 0. And you have sigma fy equal to 0. That implies ay plus by is equal to 0. Because these are the only two forces. And the sum of moments with respect to A equal to 0 implies you have 3 kilonewton times meter. This is already a moment, so we will not have distance with it. And this is clock, so I'm going to write negative. And you have a plus by times 4 is equal to 0. So because by, the line of action of by is here, and the distance from A to the line of action of force is 4 meter. So, and this is rotating counterclock. At this point of time, you should be aware of that. So it's counterclock because by, with respect to A, by is giving a counterclock moment. So that's why I have a positive. Anyways, so using this, we can solve for by is nothing but 3, and this is, by the way, meters. So 3 kilonewton times meter over 4 meter. So we get by is 3 over 4, which is 0.75 kilonewton. That's it, kilonewton. So that is by. So we will substitute by into this equation. Then we get ay is equal to negative by. That implies ay is negative 0.75 kilonewton. Because of this, you have to choose the right option. One of the options I gave you was the reaction on the left. Reaction on the left is 0.75 kilonewtons down, and reaction on the right, which is by, is 0.75 kilonewton up. So this is by, that is ay. So this is one of the questions in the quiz. So let's proceed further. So stop there. So let's look at the problem that is given on the left side. There is this beam, and there are two supports, a support at A and support at B. So when we take the beam, so the beam is like this. At B, there is a pin joint. So now I'm not going to explain the given figure. So at this point, you should be able to write that this is Bx and that is By. And this is going to be normal reaction at A, which is perpendicular to this plane, perpendicular to the plane, and this plane is making an angle 30. So NA will make an angle 30 with Y. So I'm going to have the direction, this is X and that is Y. And we need to have, I should also give you the forces. This is the force. The distributed load is 3 kilonewton over meter and it is distributed over 4 meters. So this is nothing but 12 kilonewton, right? That is nothing but 12 kilonewton. 3 times 4 is 12 kilonewton. Now that we have, and this is acting at 2 meters. This is acting at 2 meters, right? And the total length is 4. And because this length is given to be 3, so the length is given as 3 meters. We can find out this length using trigonometry, which is 3 cos 30 meters. And the height will be 3 sine 30. Because there is no gap there, what I'll do is I'll write the height somewhere here. That is going to be 3 sine 30 meters. So that is the given problem, right? 3 sine 30. Now we have to apply equations of equilibrium because we have to solve for ax, ay, bx, by. Not ax, ay, bx, by and na. We have to solve for that. So let's apply sigma fx equal to 0. So when we apply sigma fx equal to 0, tell me all the forces in x. That means we have Na sine 30 because Na is not along x or y, so you have to split this Na into its x component, and the x component will be Na sine 30 and the y component will be Na cos 30. So Na sine 30 positive bx is equal to 0. Then tell me sigma fy equal to 0. Sum of all the forces in the y. Sum of all the forces in the y would be Na cos 30 minus 12 plus by is equal to 0. Tell me sum of all the moments with respect to b equal to 0 implies. Sum of all the moments with respect to b. So let's start with 12. 12 is 2 meters away from b, 2 meters away from b, and it is going counterclock, right? It is 2 meters away from b and it is going counterclock, right? We have to follow the arrow. We complete the circle with 2 meters to be the radius, and the center is the point with respect to which we are considering the moments. So it is 2 meters away, draw the circle and just follow the arrow. 12 is going down, So on the circle, just follow the arrow, it is counterclock. So we have to write this as positive 12 times 2 because it's going counterclock. Next we have NA cos 30 and NA sin 30. Let's deal with NA cos 30. Let's deal with NA cos 30 times what is the distance? The distance is 4 plus 3 cos 30, right? The distance is going to be 4, so this 4 here plus this distance, because where is NA cos 30? NA cos 30 is here. So NA cos 30 is there, and NA cos 30 is the total distance. The distance, the perpendicular distance from B to the line of action of NA cos 30 is 4 plus 3 cos 30, and it is going clock, and NA cos 30 is going up, so it is going clock, right? It is going clock with respect to B. So we have to write this to be negative. Shouldn't we write it negative? Then only thing we are left with is NA sin 30. So we have to say NA sin 30 is the force times distance. What is the distance? Distance is 3 sin 30. What is the distance for NA sin 30, which is like that? What is the distance of line of action of force? What is the distance of line of action of force from B? What is the distance of the line NA sin 30 from B? It is nothing but the height, and the height is 3 sin 30. And how is it rotating? So you have to complete the circle like that, and it is going clock. We have to follow the arrow. So NA sin 30 is going to the right. So at this point we have to take it to be the clock. That means it is also negative, and that is equal to 0. So solve for NA. How much would NA be? So we have to solve for NA. So it implies 24 negative NA times, what is it? 3 cos 30 plus 4 times cos 30, 5.714 minus NA times, what is 3 sin 30 times sin 30? 3 sin 30 times sin 30 will be 0.75. That implies NA will be 24 divided with 5.714 plus 0.75. You will be getting 3.71, and we will be getting 3.7128. I'm going to write 3.71 kilonewtons. That is NA. So we get a positive answer. So because we got NA, we can plug NA into that equation and find BY. So BY would be NA cos 30. So 3.71 cos 30 minus 12 and times -1. So we get 8.78. 8.787, so I'm going to write 8.79 kilonewton. That is BY. We got NA, we got BY. Can we get BX? Plug in NA to that equation. then bx would be negative na sine 30. So bx would be negative na is 3.71 sine 30. So we've got 1.855. That is bx. Okay. So that will be the answer. So 1.855 kilonewton negative. That means in the problem, I assumed bx is going to the right, and I got a negative answer. So when we give the answer, you either leave it like this or you say bx is 1.855 kilonewton going to the left. So either we give the direction or you leave the answer like this, because I can see from the free body diagram that you assumed to right and you got a negative answer. Even that is acceptable. So that's how we solve a problem of this sort. Now, if you look at this problem on the left, if you look at this problem on the left, which equation of equilibrium allows us to determine FB right away? So if the question only asks you to find FB, and I'm not asking you to find AX and AY, how would you just come up with that single equation that allows you to solve for FB? The best thing would be if you take moments with respect to A, if you take moments with respect to A, then what you can do is you can take the Y component of FB. So you can take FB in the Y direction times the distance, the perpendicular distance, that is the perpendicular distance from A, and that is going counterclock, so positive. 100 times that is some other distance that is negative. So all you could use is take moments with respect to A equal to 0, and you can solve for the problem. So sometimes we have to apply smart approach. We don't need to apply the three equations when I'm only asking you to find FB. Next question. How will you, a beam is supported by a pin joint on the left and a roller on the right. How many support reactions are there? Obviously, because this is a pin joint, you have something in the X, something in the Y, so you have two reactions, and here the normal reaction. So you have three reactions. So either A or B can be right. Now, is this structure stable for all types of loadings? Now, this structure is stable only if you have a loading going down. What happens if I have a loading going up? If I have a huge load going up, this will overturn because this is a pin joint, that point. So you have to choose this. So it is not stable for all types of loadings. It is only stable for certain types of loadings. Now we apply a similar approach to 3D problems as well. So till now we have seen something in 2D. So now we'll go and apply our fundamental concepts to the 3D problems. We employ a similar approach. Wherever we have the support, we replace the support with the respective support reactions. For example, if you look at this problem, so this is a 3D problem. So in this problem, what you have is you have a rod, um, and that is a pin, and around the pin you have a joint, right, that is trying to rotate, right? So let me wait for this to sync. For example, here, with respect to this pin joint, with respect to this pin, so you have this pin, which is not visible. So with respect to this whole rod, this one here, that tries to rotate, isn't it? Let's give name of some axis. Let's say that this is X. Let's say that this is Y. And let's say that this is Z. If that is the case, my question is, what does this support do? What does this support pin, what does this do? The purpose of this pin is to allow rotation, only rotation. But the pin does not allow you to translate, but it allows rotation. Now, it's a 3D problem here. It allows rotation with respect to which axis? Does this allow rotation with respect to X? That means if it is rotating with X, the member has to have an oscillatory motion like this with respect to X-axis. Yes, it is rotating with respect to X-axis. If it were rotating with respect to Y, it will have an oscillatory motion like this. With respect to Z, you have an oscillatory motion like that. So here it is trying to rotate with respect to X. That means if we were to represent this support with respect to reactions, the way we are required to draw is we will draw the rod, what is the connecting rod, and then what we will say is at this point, right? I'm waiting for this to sync. So in the meantime, let me give the axis. Sometimes it takes a while to sync. This is X, Y, Z. So if we replace the pin, because it does not allow you to translate along X, you have reaction in X, reaction in Y, or a force reaction in Z. Also, now it allows free rotation in X, so I'm not going to represent a moment there. I'll draw a moment like this, moment Y and moment Z. Because this support does not allow you to rotate, or it does not allow the member to rotate with respect to Z axis, so there is a moment reaction mz. It does not allow rotation with respect to Y axis, so we have moment reaction along Y. So that's how we represent the support with the respective support reactions. So if a support prevents rotation about an axis, then the support exerts dash on the body about that axis. If you're preventing rotation, you will have a couple moment, only couple moment, not the force. If we are preventing it to translate, we have the force. So if the question were asking you if a support prevents rotation and translation, you have to choose option C. But for this question, you have to choose option A. When doing 3D problem analysis, you have how many scalar equations of equilibrium? You'll have 6. Because in 2D problems, what we have is sum of fx equal to 0, sum of fy equal to 0, and moments with respect to a point in the system is equal to 0, right? That is what we have in 2D. What about in 3D? We have sum of fz, sum of all the forces in the z direction is equal to 0. Then sum of the moments with respect to x-axis is 0, sum of moments with respect to y-axis is 0, sum of moments with respect to z-axis is equal to 0. So we have 6 equations in total. Now, if you see a 2D problem, which is what we have been looking at till now, if you have a problem like this, pin, a roller, right? And this is x and that is y. We were saying some of the forces in x0, some of the forces in the y0. What is the meaning of sum of moments with respect to a point? Let's take, for example, this point A. With respect to this point, everything either rotates counterclock or a clock, right? That means aren't these rotations with respect to an axis that is perpendicular to the plane of this page or our computer screen, which is perpendicular, which is coming out of the computer screen. That means, isn't it coming out perpendicular to both x and y? And what is that axis that is perpendicular to both x and y? Isn't it z? That means knowingly or unknowingly, in 2D problems, what we were doing was we were considering moments with respect to a point equal to 0, which means we are taking moments with respect to z-axis is equal to 0. So in 2D problems, this is the equation we were using. So in 3D, we will use the rest 3, sigma of z, moment with respect to x, moment with respect to y. That's what we'll be doing. So we'll be looking at various supports. For example, if you look at a ball and socket joint, you see, if we give an axis, for example, an axis like this, x, y, and z. Now, this ball and socket, what it allows is it allows free rotation with respect to x-axis, with respect to y, with respect to z, but it will not allow translation in x, y, or z. So how do you represent the support with respect to support reactions? Because it will not allow this member to translate in x, you have fx, fy, fz. That's it. So does it allow rotation with respect to x? Yes, it does. That is why we will not have a moment reaction. Does it allow rotation with respect to y? Yes, it does. So we will not have a moment reaction. Does it allow free rotation with z? Yes. So we will not have a moment reaction. So this is how we represent a support with support reactions by understanding the support. That means we have to understand the support. For example, if you look at this, let's consider that this is x, this is y axis. Let's say this is x axis and going perpendicular, this is z. I mean, it's hard to understand. What I'm going to do is I will give, let's say this is x axis and let's say this is z axis. Now tell me, this is a bearing. By the way, the support which I'm showing you here, it is a journal bearing. There are two types of journal bearings which I will discuss. One is a smooth journal bearing. The other one is a thrust journal bearing. Now, when we say smooth, so what's the purpose of a bearing? Bearing allows a rod to rotate. A bearing allows a shaft. If there is a shaft going through the bearing, it allows the shaft to freely rotate. So it has least resistance towards rotation, or it allows rotation, but it will prevent it from translation. For example, here it will prevent translation along x, so you have fx. It will prevent translation in z, you'll have fz. Some bearings, you know what they do? They prevent a translation along y. Some of them they don't. That means translation is free along y. But for some, translation is not free along y. For those cases, you have a reaction in the y. How do we know that? If I say thrust bearing, that means there is no free translation. That means you have a reaction force along the axis of rotation whenever I say thrust. But when I say smooth journal bearing, smooth journal bearing allows things to translate. This one prevents translation. So we have to read the problem carefully. So if I just say journal bearing, what we have to understand, it's a smooth journal bearing. But when I say thrust, I'm going to specify clearly that it is a thrust bearing. That means it prevents translation. So look at this figure here. Does it allow the shaft? Now, where is the shaft? The shaft is this one here. This is the shaft. So it is going into, coming out. This is the shaft. Now it is inside. That's the shaft. Now, is the shaft free to rotate with respect to x? That means, can it rotate like that? Is it free to rotate? No, it is not. That means we have a moment reaction with respect to x-axis. That means we have to say mx because it is not free to rotate. What about y? Is it free to rotate with y? That means can it rotate like that with y? Yes, it is. That means we don't have a moment reaction with y. What about z? Is it free to rotate with z like that? No, it is not. Hence, we should give a moment reaction mz. So should we give the force reaction Fy? It depends on the bearing. If it's a smooth bearing, we don't need to give this force reaction. So only thing is we give the force reaction in X and Z, but no force reaction in Y and no moment reaction with respect to Y axis. So we have to understand the support before we replace the support with respective support reactions. So even in this problem here, which you see, so here there is a smooth, there is a, let's say there is a slab connected, attached to the wall, but we also have a rope support going from B to A that improves the safety of this slab from falling. So for example, we have the slab, so we have the slab. Now we have a rope going from B to A. Let us represent the rope with tension A. Now let's take a similar arrangement, and what I'm going to do is I will prevent, or I will have a different arrangement. So it is going from B to, let's say this time it is going to D, like that, tension D. And let's say this is the weight, this is the weight. Now tell me, in which case A or case B? In which case the tension of the rope is higher? Well, the question is TA is equal to TD, or TA greater than TD, or TA is less than TD, or none of them are? What can you say about that? So the higher the slope of the rope, so this rope slope is bigger than this one. Higher the slope, lower its tension if it is required to, if it is supposed to balance the weight. Higher the slope, lower its tension. Why is that? For example, apply sigma Fy equal to 0 for case A. What do you get? So this slope is higher. That means this theta, slope means theta. If theta is theta A, and let's say this is theta B, okay? So sigma Fy equal to 0, isn't it Ta sine theta A minus W is equal to 0. That implies what is TA? Isn't it W over sine theta A? Similarly, when you apply sigma Fy equal to 0, for this case, isn't it TB sine theta B minus W is equal to 0? That implies TB is nothing but W over sine theta B. Right? I'm waiting for it to sync. It takes a couple of seconds. So, oh, it is taking forever to sync. No, it's not syncing. Here you go. It's synced now. So here you go. So, for example, TA, if you apply sigma phi equal to 0, TA sine theta A minus W, then W or sine theta A here, W or sine theta B. So I said theta A is bigger than theta B. That means sine theta A is bigger than sine theta B. So if you're dividing this with a bigger number compared to sine theta B, what happens to TA? Because numerators are both the same, so TA will be less than TB. And TB or T, oh, I use TD there, it's fine. I use TB here. What I mean to say is TA is less than TA is less than TD. That's what I mean to say. So that means this is the correct option. That means to do the same job, if you're using the same rope material, just by changing the design, just by changing the geometry, we are making sure that the tension developed in the rope is lower just because of a small change in where you're attaching or how you're attaching the rope. So that being said, we have to design when it comes to design, we have to use right technique to design. So the design we form will be safe. Okay, then let's look at a case here. If I'm asking you, there is a floor crane, draw the free body diagram of the floor crane. That means you take the crane. This is the crane. This whole thing is the crane. This whole thing, this whole member, that's the crane. Then if I ask you to draw the free body diagram, only thing is you remove the support. What is B? B is a roller support. What does a roller do? A roller is free to move in X and Y, but it is not free to move in the Z. So you have BZ. Similarly, you have AZ. Similarly, you have CZ. Similarly, at the center of gravity, you have the weight of the crane going down, right? Then this is the weight of the drum. This is the weight of the drum. The floor crane weighs 350, so this is given as 350. So what is the maximum weight of the oil drum? WO. How much? What is the maximum WO that it can support? How will you do this? when it is supporting a maximum weight, what happens to this arrangement? So as you keep increasing W, so you keep adding 1 pound, 1 pound, 1 pound, 1 pound slowly. Let's say there is a 2,000 pound, let's say it became 3,000 pound. At one point, it would start to rotate, right? Or it will lift off at C, isn't it? It will lift off at C. That means what happened, what is happening to CZ? When it lift offs at C, that means it is no longer touching the ground at C. That means CZ will be equal to 0. So indirectly, the question is asking you to find W naught for which CZ becomes 0. That means all you have to do is once you write the equilibrium equations, that means sigma fx equals 0, sigma fy 0, sigma fz equals 0, moments with respect to x-axis equals 0, moments with y equals 0, moments with respect to z-axis equals 0. What you do is you plug in CZ equal to 0 in those equations and solve for W naught. So by reading the question, you have to understand. So that is how these 3D problems are advantageous. So this is how we do any of these 3D problems. If you look at this, there is a smooth surface support. How do you represent this? Because this is touching a surface, you draw a normal reaction force that is perpendicular to the surface. What about this journal bearing? Like I said, if I say single journal bearing or smooth journal bearing, it is free to move or translate in that direction. Also, it is free to rotate in that direction with respect to that axis. So if you look at the free body diagram of that support, there is no force along that axis of rotation. Also, because with respect to that axis, it's free to rotate, there is no moment reaction. But with respect to the other two axes, you can translate, so you have fx, and you can rotate, you have mx. You can translate, you have fz, you can rotate, you have mz. Similarly, try understanding how a hinge works, how a ball and socket joint works. So by looking at a problem, so what is the difference between the hinge and journal bearing? Now this hinge, it will not allow it to translate in that direction. So you have fy, but it is free to rotate with respect to y-axis. That is why you have no moment with respect to y, but it is not free to rotate with x, it is not free to rotate with z. So you have mx, mz. One important note before we proceed further is when you have journal bearings or when you have hinges, look at the journal bearing. How do you represent a journal bearing? Right? This is x-axis, this is y-axis, that is z-axis. Now tell me, this part of the rod, this is a twisted or a bent rod, that part of the rod, what happens to the support at A? When you take A, what happens to the support at A? Like I said, I represented the x-axis, I represented the y-axis, and I represented the z-axis. And I said it is a smooth journal bearing. So when I say smooth journal bearing, it is free to rotate in that direction. That means you have no moment reaction in x, but it is not free to rotate in y, and it is not free to translate along y. So there is a reaction in y, or I'm going to say this is at A, so I'm going to just say AY, and there is a AZ. Now, if you observe the free body diagram, there is no moment reaction given. Why? That is something that I'm going to discuss now. In a system, if you have two or more properly aligned bearings or hinges, we only draw the force reactions, no moment reactions. That means here, you see, this is a bearing, journal bearing. This is another bearing. That is another bearing. If you have these two bearings, just look at A and B. Imagine there is no C. When you have A and B, can you pull the rod up? Can you move up? No, because there is AZ and there is BZ that prevents the rod from going up or down. What about in the X direction? That means in this direction. That means in you have B. Don't you have BX there? Because this is X direction, this is Y, and that is Z. You have Bx that prevents it from translating in X. You have Bz prevents translating in Y. You have Ay that prevents translating in Y. Now, what about rotations? What prevents the rod from rotating with respect to y-axis like that? Not just this journal bearing, BZ. You see this BZ? This reaction, prevents the rod from lifting off. That means rather than the moment reaction at A, BZ is what supporting or causing a moment reaction with respect to A because BZ is acting at certain distance away from A. So what I'm trying to say is when you have two or more properly aligned bearings, two or more, when you have two or more properly aligned bearings, you're not required to draw moment reactions. That means this kind of moment reaction with respect to y or this kind of moment reaction with respect to z. We don't require to draw those. When two or more properly aligned bearings are present, it is not required to draw the moment reactions. It's not required to draw the moment reactions. But if we have only one, for example, look at the case here, you only have one hinge. Yes, this is the hinge. This is the only support present in the system that has to prevent the system from rotation. Now, this one here allows free rotation with respect to that axis, isn't it? With respect to that axis, you can, with respect to this axis, you can freely rotate like that. That is why you have no moment reaction with respect to y, but with respect to x, that means if this is x, rotation like this is prevented. So you have moment with respect to x-axis, you have moment with respect to z-axis. So moment reactions are given because there is only one hinge or only one bearing in the system. You have to draw moment reactions. But if there are two or more properly aligned, you are not required to draw the moments. Okay. So with that being said, how many equations of equilibrium do we have? We have 6. We can go ahead and solve for the problem.